Okay, so hello everyone, and this is Chipmaster, and in this video series I'll be working on a desktop motherboard that another tech bought it off eBay, and it's not turning on. So he bought a board, and the board that he bought off eBay isn't working. So he decided that he wasn't going to send it back. So he took it to me to see if I could repair it and save him that extra cost and headache to get it back to the supplier. Alright, so this is the box. As you can see, it's an Asrock, right, Z270, right, Pro 4, and it's a socket 1151, he said, CPU socket, and it's a, as you can see, alright, so it's a 8th generation, right, socket 1151. Motherboard. Alright, so you see that it's not turning on, so I will do an inspection and see what's happening. Alright, so as you can see, the board is here. You already left the RAM and the CPU in it. Okay, so as you can see, the board is out. Alright, so first I will just get the power supply. Alright, so I'll first do some resistance checking on the board. Okay, so I will now get the multimeter ready. Okay, so first, alright, so first of all, as you know, this is a socket 11 CPU, and the CPU that's inside is a 7th generation CPU. As you can see, it's a i7-77K. The K means that it supports overclocking. Right, so this is a 77K, 770K. Right, so it's a 770K i7, 4.20 gigahertz CPU, and the K indicates that overclocking is unlocked inside of the CPU. Alright, so it's overclockable. Alright, so I'll now check some resistance. Alright, so this is a PCI Express slot, right, and there's another PCI Express here. So we have two PCI Express slots here. Right, so first I'm going to check the resistance. Oh, that's too bright. Alright, so first, so the PCI Express slot is having two sides. So you have A side, with the side that is to the CPU, right? The side that's to the CPU is the A side. The side that is point to my direction is the B side, right? So please bear that in mind. All right, so I'm going to check on the B10 pin. So this is A, and this is B. So A1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the resistance is 252. Okay, all right, so this is a seventh, as I said before, seventh generation, and this is a 200 series, as you can see, Z270M. So that indicates that it's a 270 or 200 series chipset, right? So the CPU is matched or paired with the 200 series chipset, and the Z indicates that it's the high grade, right? This is the highest of the chipset. We have B and we have H series. So this is the Z series from Intel, and this is the ZM270, right? So this is ZM270, which is, as I said before, which is a 200 series PCH, right? So I'm checking B10 and it's all clear, right? So this is the standby 3.3 voltage, or you can call it VCC PRIM 3.3 volt standby for the PCH, right? We have a coil here. As you can see, this is most likely 1.0 volts. Let me check the resistance, and we get 30, right? And that's 33, and that indicates a good resistance there, right? I'll remove the CPU. Alright, so I'm going to remove the CPU from the socket. Okay. Alright, so I already checked 1.0 volt there. VCC PRIM 1.0. So this is another standby rail for the PCH, right? VCC PRIM, and I get 33. Now I'm going to check another coil here on the RAM side. This is most likely for VPP voltage. This is 2.5 volts for the RAM, which is one of the secondary power supplies for the RAM, right? So I'm also checking, I'll have to move here to check the CPU core. Remove this heatsink. This heatsink is used to cool the upper MOSFETs during the switching process, because the CPU takes a lot of power. So this is the MOSFET will switch at a very high frequency to provide the power supply that the CPU demands. So it must meet the demands of the CPU in order to provide proper power delivery for the CPU. Right, so I'm just removing this heatsink. As you can see, heatsink is removed. Right, so here we have some coils, and each coil here is a phase. Right, so we have 1, 2, 3, 4, 5, 6, 7. Right, so these are most likely in parallel, and this is for the VCC GT, which is the integrated graphics. Right, this is most likely for the system agent VCC SA, and the other 4 should be for the CPU core. Right, so I'm checking on the upper MOSFET source, and I'm also checking the drain pin to check the 12 volts per supply. As you can see, I'm getting 552. Right, normally if you put the CPU back inside of the socket, it will be a bit lower. Oops. Alright, let's check again. As you can see, I'm getting 1 there. Alright, so that indicates that the CPU ground pins is also used as a form of grounding. So it's always good, important to take the CPU out when checking these resistances. Alright, so I'm checking the 12 volt line here, as you can see. Sorry, this is ground. 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 And that's not normal. So I'm checking here, I'm getting ground. Let me check here. At 37. Upper MOSFET. 42, 47, 48, 50. Center pin here, is it correct? I'm getting ground on both sides. Alright, this side is the ground side, and this side is the power side. But I'm getting ground, that's not normal. As you can see, I'm getting ground here. Alright, CPU core supply. Alright, that's the lower MOSFET, sorry. And I'm getting a short here. So something is wrong here. Alright, let's check the RAM core supply. As you can see, I get 26. Let me remove the RAM. Check again. 45 resistance here. Alright, I already checked. This is 5-volt dual. This 5-volt dual. Let's check 5-volt dual. 5-volt dual is also good. So VPP is good. Alright, VPP is okay. VCC PRM 3.3 volts is okay. VCC PRIM 1.0 volts is okay. But the CPU core section is not okay. And the core supply for the RAM VDDQ is okay. Right, so I'll check again. This is the CPU power connector from the ATX power supply. So this is the ATX plus 12 volts. Oh, it's okay now. That's weird. I wasn't getting any resistance there. I was getting 0.00 voltage drop there. Okay, so it's normal now. Let me put back one of these, right? But it was impossible because I was getting a short to ground. It's impossible. Alright, so check in here again. This is the CPU core. Alright. Oh, come on. And this is the ATX plus 12 volts that I'm measuring there. This is VCC SA. This is VCC IO. As you can see, another regulator here. And this should be VCC IO. Sorry. Alright, VCC IO is okay. This VCC also good. And VCC GT, the graphics. And we get 48, also good. Alright, and these are the upper MOSFETs, VCC GT. Okay, so before I was getting a low resistance here, which was abnormal, but it's now cleared. I don't know what happened. After removing, I was checking 5-volt dual, core supply for the RAM, VDDQ, VCC PRIM, RIM 3.3, VCC 1.0, VCC PRIM 1.0 volt, standby for the PCH is also okay. But I was getting a low reading on the CPU core. Alright, so I'm gonna plug the power to the board now. Get the power supply cable. okay. So I'm gonna check some voltages now. Alright, so first I'm gonna check VCC standby, VCC PRM B10. So B is A 1, 2, 3, 4, 5, 6. Sorry, sorry. Let me go again. Just A 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm not getting 3.3 volts here. On some boards, on some of these boards, the PCH, after getting the SLP source signal, then it will take the 5 volt standby, which is coming from the purple wire here. Let's check if we're getting 5 volts. Oh, I didn't switch on the power supply. That was my mistake. The power supply wasn't turned on. Let's check again. B10. Now I get 3.3 volt, 3.4 volts. Right, so that indicates I'm getting 5 volts here. Right, this is the 5 volt standby. Right, so 3.3 volts is okay here. That means the PCH has already released SLP source signal from the PCH to another regulator, and then from that regulator to the B10 slot of the PCI Express slot, and also give the EC, the IO, this is the IO, so the IO controller gets 3.3 volts as well. Right, so let's check if we're getting 1.0 volts. Yes, we're getting 1.05 volts here. This is the standby secondary one VCC PRIM standby 1.0 volts for the PCH. Right, so we have voltage in order to get trigger now. Right, so the PCH has its main standby, which is VCC PRIM 3.3 volts. We have VCC PRM 1.0 volts. So I am assuming that the RTC section inside of the PCH is okay. So that's VCC RTC, SRTC reset, 32.768 kilohertz. Right, once those 4 working conditions is okay, the CPU will immediately get the deep sleep well, which is the VCC DSW VRMEN. Right, so that's a deep sleep VCC underscore DSW, right, underscore 3.3, and then it will release DSW power OK signal back to the IO. So the IO will now wait for the switch. So let's check if we're getting 3.3 volts at the switch. And this is here on this section here, as you all know it, on a typical desktop motherboard. Board is so big. I'll have to zoom out. Zooming in won't work. Board is too big. Alright, so 3.3 volts here. Right, so the switch has 3.4 volts, as you can see. Alright, let me just carry this up a bit. Let's move some stuff. So yes, so the switch has 4.4 volts here, so that indicates that the PC has standby. So I'm going to use the tweezer here and see if I can trigger this board. Let me get the CPU, the fan, so I can know if the computer is actually turning on, because I'm not using a DC power supply to see the current. So I'll have to use this fan to see if the fan spins. And if the fan spins, then I'll know. So as you can see, I short the pins, but it's not turning on. And the fan in the power supply is not turning on either. Right? But this is for demonstration purpose. I want you to see when the fan spins. So as you can see, let me turn off the power supply. Turn it back on. Right? And I'm touching the 2 pins together, which is the power button and ground, and it's not turning on. For some boards, if the CPU is not sensed, then it can't turn on some boards, right? So I'm going to put the CPU inside of the socket because there's a signal which is called the socket SKTOT underscore SOC signal, which is sent to the EC to tell the IO, sorry, to tell the IO that the CPU is present. Alright, so I'm putting back the CPU back inside of the socket. Alright, so let's go again. See if it can turn on. So this is the original problem of the laptop, of the computer system. Right, I won't connect the 12 volts at the moment. I just want to see if the fan are spinning. Still doesn't spin. Right, so it's not triggering, so this is a no trigger fault. Even though I have standby 3 volts, 1.0 volts. So I'm going to check the RTC section now inside of the PCH to see if the PCH is receiving RTC well and DSW or deep sleep well signals are generated. So first here we have a crystal here. There's a crystal, a 32.768 crystal, which is beside the PCH. So I'll plug in back the power and I'll check there. We should get 0.2 volts on one side and the other side should give you 0.34 or 0.35 volts. So the voltage on both sides of the crystal should not be the same. Alright, so this is the crystal and I'm getting, oops, turn on the power supply. And I'm getting 0.4 volts on one side and the other side is giving me 0.3. So as you can see, you should not get the same voltage. 0.4, 0.4, voltage should be different. 0.39, 0.3, 0.4. So I'm getting the same voltage. Now I'll have to use oscilloscope now to check if I'm getting a waveform, because most times the voltage on the RTC clock should not be the same as the voltage of the RTC crystal. Voltages should be different on both sides. Alright, so I'm just setting up the oscilloscope now to capture this clock signal. Alright, here we go. Let's see if we're getting some clock. Yes, and we got clock. Alright, so let me connect the RTC battery. Let me connect an RTC battery first and see if I'm getting. It's best to check with the RTC battery in. 2.9 volts here on the RTC battery. Alright. Oh, let me turn down the aperture. Alright. That's the supply line and the ground point. Alright, so let's check. And I'm not getting any wave whatsoever. I'm not getting any waveform. No waveform on the RTC section. No wonder why I was getting the voltages on the same side. So if you are getting voltages and no signals, say voltage is there and no waveform, could it be that the crystal is bad or the PCH is faulty? Let me check one more time. Alright, and I'm not getting any waveform on my RTC battery. My RTC battery is 2.9 volts, as you can see. Alright, so I'm checking the RTC battery here. As you can see, the RTC battery is 2.9 volts, which is a 3-watt battery, which is sufficient to turn on the internal clock oscillator inside of the PCH to turn on this crystal. Right, as you can see, I'm getting 0.4 on one side, and the next side I'm getting 0.4, which is not correct. I should be getting 0.3, and the other side should give me 0.4 volts. So I'm getting 0.4 volts on both sides. So this indicates to me, as you can see, there's a delay. There's a delay there on one side, and the other side give me instant 0.4. The other side I got a delay. See that? 0.3 for a few milliseconds, and then back to 4. So that indicates that I'm having an issue with my RTC well section, as you can see. Right, so I'm checking the crystal on the oscilloscope again. Right, so let's take a look at the oscilloscope one more time. As you can see that there's a problem there with the RTC section. Sorry about that. Just try. Alright, so I'm checking. No wave. Next side. No wave. Alright, so there's a problem. So I'm going to head over to the board view. I don't think there's a schematic for these types of motherboards. I don't think there's a schematic for these boards, so I'm gonna check for the board view. Okay, so I'll now go under the microscope now. Alright, so as you can see, this is the circuit that we're looking at right here. So this section here, as you can see, which is that OR diode. So this is the OR diode, as you can see. So this is the battery voltage. So let's go over back to the meter. Alright, so I'm checking the battery voltage now and I'm getting 2.9, and this is the resistor. I'm getting 2.9, coming through the resistor 2.9, and then it's going to come through this diode here, which is this side of the diode, and it will exit in the diode. We get 2.7. Remember, this is a germanium diode, so it will steal some of the voltages, right? So if the voltage for the RTC section is below 2.4 volts, then it's not a valid RTC supply, because the RTC reset will be delayed too long, so the valid time for the RTC section to be reset is 18 milliseconds. So if 18 milliseconds is passed and the RTC well is not reset, then this will cause no trigger, right? And the RTC section won't work because the delay is too long. And that's normally caused by a capacitor which is connected to the RTC reset, which is normally a 20k resistor through a 1 microfarad resistor, and that's 1 multiplied by 20 should give you 20 milliseconds. So if the resistance of the RTC section is not delayed, or the RTC section of the delay circuit is not within 18 to 20 milliseconds, anything after 20 milliseconds will become an invalid reset signal, right? So this is 2.7 volts, and that's within the threshold, right? So if it's below 2.7 volts, then you will not have a valid reset signal. And then again, let's go over to this part of the resistor. So I'm going back now. I'm going to remove this part of the, I'm going to unplug the I'm going to remove this shield that's over the PCH. Alright, so I'm removing the shield over the PCH here. Alright. Down. So as you can see, this is the PCH, the Z270-200 series PCH, which matches the 7th generation CPU. Alright, so I'm just inspecting the PCH. At the top of the die here is normally easy to crack, so I'm removing that thermal paste that is kind of a bit hard on top of the PCH here with some 99.9, just to examine the PCH if there's any crack around this section, because these PCH always crack after a period of time on the die here or on the core, or we can call it the heat spreader. This is the integrated heat spreader here. We normally call it the die, and it's looking okay, right? There's no crack on the die. Let me zoom in on the die. Right, so the die is intact, there's no crack, as you can see, so it's intact. Alright, so I'm going back under the microscope now. Alright, so let me go back to the board view. So we'll so as you can see, we checked here as far as here, so we get 2.7 volts here, and it's coming to this capacitor here and then to this resistor as a pull-up resistance to reset the RTC reset signals, as you can see, right? So this is a resistor, and this is another resistor, which is SR289, and this is another pull-up resistor, and this is going to turn on the intruder. This signal is not really used anymore. It was used back in the earlier PCH of ICH4 with the dual core CPU of the Penryn, right? Which is the Penryn CPU, which is the dual core CPUs before the Core series came out with the Arundel CPU of the first generation of the Core Intel series CPU, right? So this signal is not really important anymore, right? So what the key signal that you should focus on is the RTC reset and the SRTC reset signals. Alright, so I'm going to look at this resistor here. Let me turn it around from this angle that I'm looking at. Okay, I'm looking at it from this angle so I can locate the component easily. Alright, so it's Alright, So let me go back for the enter. Alright. Okay, so here is the resistor we are checking, and I'm getting 2.7 volts, and this side is also 2.5. As you can see, it is a bit pulled down, right? So it has gone from 2.7 to 2.5 volts, right? And RTC reset signal, and here is it again, 2.7, and this is 2.7 volts, 2.7 volts here, and that's a pull-up, and these are the two resistors. But this side I'm getting 2.5 volts, and that's a bit too low. Well, it's not, it should not be below 2.5 volts. 2.4 volts is the threshold. So I'm checking here, and this is intruder. Oh, this is a one, this is normally a 10 mega ohm resistor, as a 1 mega ohm resistor, as you can see. So that is why it's taking some of the voltage, because it's a 1 mega ohm resistor, so that's normal. So this is the one that you should be focusing. So this one is okay. Here is 2.7. I measured here and I get 2.7. Right? So that section is okay. Let me zoom out a bit. Alright. So that's good. So we need to check here as well. So we have, so here is okay. So this is the intruder where we're getting 2.5 volts. This side is a pull-up. So I'm getting our SRTC reset is okay, is resetting. We need to check the next reset signal now. Let's check this resistor. And this resistor is SR403, and we have VCC RTC there. Right? And this resistor, this is a capacitor C49, and this is VCC RTC section. And here, this is another, this is a test point. Ground. And we have ground here. Okay, so that side is ground. Alright. And here now, let's see what over here is. Remember, there is no schematic for this board, so we have to use the board view. Case open. Alright. This one is ground. This is a capacitor. And that's a diode there. And that's a resistor, OR9. And that's not important. BR2. And we have net. I don't know what that means. And we have a capacitor here, BC2, BR3. And here is RTC reset. So this is another signal, another important signal. This is the main reset signal for the RTC section inside of the PCH. And this should be a pull-up, and this is the capacitor. This is a 20K resistor. It's a 30K resistor. It's normally should be 20K. I think that's an error. That's a mistake in the board view. This should be a 20 kilo ohm resistor, and this should be normally a 1 microfarad capacitor, as you can see. So it's 6.3 volts, 1 microfarad capacitor, and this should be a 20K resistor. I'm going to measure this resistor in the, shortly, but it should be 20 kilo ohm because it's a pull-up resistance for the RTC well. So if this resistance is too high, then the delay circuit will not. The delay circuit will be too long, and the RTC well section will not have a valid reset signal. So I'm going to check here under the microscope. Alright, so I'm going down that side on the board here. It's over here, right in this section here. So here is it. This is the resistor. Focus a bit more. Alright, so that's the resistor here. Let's see if we're getting 2.7 volts there on both sides. So this side I have 2.7 volts, and the next side I have 2.7 volts. Very good. So the RTC section is powered. So VCC RTC is powered, SRTC reset is powered, RTC reset is powered, right? And this is the capacitor, which is a 1 microfarad capacitor. Now let me measure this resistor. It should be getting 20K here instead of 30. No, it's correct. So for the Intel, so this one is normally for the laptops, it's 20K. So on the desktop, it's 30K. Interesting. uh, so my RTC well is powered. So let me check the crystal. Alright, here's the crystal SX2, and I wasn't getting any waveform. I'm getting 0.3, and then it goes to 4, and then this one goes straight to 0.4, but I wasn't getting any waveform. So RTC's VCC RTC is okay, RTC reset is okay, SRTC reset is okay, but 32.76 kilohertz is not okay. So first we normally have to check these picofarad capacitor. These are normally picofarad capacitor. As you can see, they are white, and this is normally a 10 mega ohm resistor. So I'm going to check this resistor, making sure that it's 10 mega ohm. Okay, so it's 10.2 M, as you can see there. Alright, so let's go again. So it's 10, 9.9. So it's in the range, so the resistor is good. So let me see here. So the crystal, I'm going back over to the oscilloscope again to check, and I'm going to check with the power inside. Huh? Alright, let me check. I think my trigger level is too high. Oh, there we go. I'm not getting the resistance. I'm not getting the waveform. My trigger level was too high. So as you can see, if you can see, I have 32. Oops. I have 32.1. Alright. I have 32.1 here. On the next side. So on the next side I have 32.9, and the waveform is beautiful and intact. So the RTC well is okay, as you can see. Alright. So let me go out. Alright. Okay, so the RTC well is okay. So the RTC well is okay now. I was on my trigger level was too low. That was why I wasn't getting the waveform. I should be at 200 millivolts on the trigger level. I'm going to try and power the board again. Alright, good. Oh, the fan is spinning now. What the hell? So the RTC section, so the PCH, after removing the die, sorry, the heatsink, it's turning on. So it is something wrong with the PCH. So it was on the PCH side, why it wasn't triggering. Interesting. Let's try again. As you can see, the fan is spinning now. Let me just connect the heatsink on the CPU. Alright, there we go. Alright, so I'm just going to, oh sorry, I always forget to turn on that switch behind the power supply there. Okay, there we go, now it's working. So the PCH, it seems like the die, the PCH had an issue because it wasn't turning on. So let's check if we're getting the basic voltages. So first let's check RAM supply, 1.2 volts. Or let me go over to the multimeter. Alright, RAM supply. This is a DDR4, fourth generation RAM. Right, 1.2 volts is there. VPP 2.5 volts is there. Excellent, 2.5 volts is there. Okay, am I getting VCC SA? Let me check. VCC SA 1.0 volts. Oh, sorry, I didn't connect the additional power supply for the CPU. ATX 12 volts. So let's connect the ATX 12 volts. There we go. So the ATX 12 volts is intact. Alright, let's go again. Let me zoom out a little bit. Too much. One more zoom. That should be it. Alright. There we go. Alright, so let me go again. Oh, it's turning on every time now. Beautiful. Alright, so first let's go back again. So standby, it's 3.3 volts. It's there. Excellent. RAM supply, 1.2 volts. Excellent. VPP 2.5 volts. Excellent. 1.0 volts for the PCH standby. Very good. Am I getting VCC SA 1.0 volts? Yes, VCC SA is there. Alright, CPU core is there, should be 0.8 volts. Am I getting it? CPU core 1.3, that's too high. That indicates that the CPU is not starting. The RAM is not in as yet. Okay, so the RAM is not in. Let's see if we're getting termination supply 0.6 volts. Yes, excellent. 0.6 volts is okay. Alright, so but the CPU core is a bit too high. So let me check if I'm getting this VCC SA and VCC ST. This should be 1.0 volts, sometimes 0.9 volts depending on the board. Alright, VCC ST supply is okay. Was okay, and that's good. Let me plug up because I need to move this cord out of the way so I can connect it the other side. I have to do it this way. Alright, so I'm going to trigger it again now. Oops, too close to the, I was zoomed out a bit. Alright, a little bit more. Alright, there we go. Ah, it's turning on every time. Beautiful. So it was the heatsink and the PCH is hot? Yes, relatively hot. Okay, so yes, so VCC ST and VCC SA is okay. This is VCC ST supply. Right, 1.0 volts. VCC SA 1.0 volts. Excellent. But the CPU core supply I was getting. Oh, sorry, this is the CPU core. Oops. Oh, you see that? This thing can be frightening sometimes. And I'm not getting any voltages here. Let's check if we're getting 12 volts. ATX 12 volts. Yes, ATX 12 volts is there. CPU core. Let's see if I'm getting 12 volts at the drain pin. 1.3 volts. And I'm not getting any voltage for the CPU core. .3 volts. It's abnormal. Let me pause. Alright, sorry, I had to answer some text messages a while ago. Alright, so I was saying that I was checking here, but I'm not getting the CPU core. What in 1.3 volts? It should be 12 volts here. Let's check if the CPU is properly seated inside of the socket. Yes, CPU is intact in the socket. Let's check in the pins. Pins are intact. Just turn it on. Alright, the CPU is getting hot. Yes, it's hot enough. Alright. Alright, so checking the core supply. Where I should get in 12 volts, I'm getting 1.3 volts. That's abnormal. Let me do it without the CPU in it and see if it can turn on. Let's check the resistance to ground on the 12 volt line. That's 38, 39. Let me connect the RAM first. Alright, so connecting the RAM. Let's check and see if I'm getting the CPU core voltage, because I wasn't getting the CPU core. I'm getting 1.3 volts each time we're supposed to be getting 12 volts. I'm getting 1.3 volts, which is abnormal. I just want to see if the fan spins. Alright. Alright, so I give power. Alright, so let's check. .3 volts. 12 volts is there. Yes, I'm getting 12 volts. So this is the reason why the CPU core wasn't coming, because of the RAM wasn't there. This is the process called ERP, which stands for Energy Saving Product, or EUP, right? So this mechanism was developed by Intel, right, and Gigabyte and ASUS, right, to design this technology implemented inside the motherboard to conserve power, right? So once the RAM is not in, then it will not produce the CPU core supply. As you can see, now I'm getting 1.3 volts for the core supply. Sorry, right here. Am I getting ground? Right, core supply is there, 1.3 volts. Alright, very good. And I'm now getting the 1.3 volts. See, 12 volts. And I'm now getting 1.3 volts there. Alright, so I'm going to connect the heatsink now. There we go. Alright, let me just connect these. Alright. Alright, so I'm gonna check CPU core again. Alright, 1.3, 1.3, 1.3, 1.3. Let's check if I get in PLT reset signal A11. Yes, I'm getting PLT reset. Alright, PLT reset is there, 3.3 volts at the A11 pin of the PCI express slot here. Alright, 3.3 volts is there. Excellent. So I'm getting 3.3 volts. Let me Try the next slot. Okay. Checking the CPU core. 1.2. I'm getting 12 volts there. 1.2. 0.2. VCC SA. 1.0 volts. That's 12 volts. Very good. 12 volts CPU core. 1.2 volts. And I'm getting reset signal. RAM supply, all supply is there. So that indicates to me that the board is ready. So I'm going to connect the keyboard now. Alright, so I've connected everything. Alright, so just checking if I'm not getting a display. Connecting one RAM for now. There we go. So I'm getting caps lock, as you can see. So it's working now. Alright, there we go. Alright, so the caps lock is there. Look at that. Sweet. See that? So that caps lock indicates that the computer is fully working. Alright, let me just check this RAM. Try again. So it doesn't work in this mode. Alright, so the daisy chain won't work. Alright. Okay, so I see we have a RAM issue here with this one, so I'll have to clean the contacts with a pencil eraser, with that eraser, and see if I can get this. Not getting the caps lock, so it seems like something is wrong with the RAM. Let me check the other slots to confirm. Seems like if something is wrong with this slot, because this RAM worked in this slot. So I get in the caps lock. Still no caps lock. No caps lock. Nothing. Trying the other slot. Oh, there we have caps lock. Alright, so let me try both RAM now in these two slots here. Oh, look at that. Yes, we have display there. So that's a fix. So it's working now. So it was caused by a tension that's under the heatsink. So I'll put some fresh thermal paste here. Right. So as you can see, it's very tough and dry here. It's kind of a bit hard. So I'll put some fresh thermal paste here on the heatsink. Alright. So I'm just removing the old thermal paste here. It's a bit tough, hard. Alright, there we go. Alright, so I've removed it. Alright. Alright, so I'm going to power it one more time. I like to see where that fan spin when each time I turn on the computer, this board. Ah, look at that. Look at that. And it's working now. So the job is done. The job is done. The job is done. Alright, so wasn't that difficult that I expected. So the heatsink, so I realized with these Intel chipset, after a period of time you'll have to remove the heatsink, remove that old thermal paste, because it's, after a while the heat on the top of the die there, or the integrated heat spreader, will cause that problem after a few years. So I recommend that you do this after a couple of years. Remove that heatsink, remove the old thermal paste, put new thermal paste on it, because you'll end up killing that thing, which is the die, and it can crack, and then you have to replace the PCH, right? And not many people with the skill set to use a BJ machine to replace that. So now we'll have to replace the motherboard. So I hope you learned something, and I hope you enjoyed the video, and I see you again when I'll fix something for you in the next video. Okay, bye.